This online tutorial is about the leveling effect of amphiprotic solvents. In the previous video, I discussed the leveling effect of water in aqueous solutions. Here, I'm going to discuss leveling effect of amphiprotic solvent in its general form, applicable to both aqueous and non-aqueous solutions. This discussion is very similar to that of aqueous solutions. Based on IUPAC's Goldbook version 2.3.3, we can say that the leveling effect is the tendency of a solvent to make all Brensted acids whose acidity exceeds a certain value appear equally acidic. It is due to the complete transfer of a hydrogen to a protophilic solvent from a dissolved acid stronger than the conjugate acid of the solvent. The only acid present to any significant extent in all such solutions is the ionium cation of the solvent. Due to the leveling effect of solvent on acids stronger than the conjugate acid of the solvent, solutions of such acids at the same concentrations have the same acidities. A corresponding leveling effect applies to strong bases in protogenic solvents. Let's consider HS as the general form of an amphiprotic solvent, where H is for its ionizable hydrogen and S is for the remainder of the solvent, or S is for the first letter of the word solvent. Here, we should not mistake S with sulfur. Also, for a protogenic solvent, which is a solvent capable of acting as a proton donor, and for a protophilic solvent, which is a solvent capable of acting as a proton acceptor, I'm going to use this HS. Based on our previous discussions, we know that amphiprotic solvents can act both as proton donors and proton acceptors, or amphiprotic solvents are both protogenic and protophilic. For an amphiprotic solvent, we can consider two conjugate acid-base pairs. One is H2S plus HS, and another one is HS minus. Here, H2S plus is the ionium cation of the solvent HS. It is the conjugate acid of the solvent. It is produced by protonation of the solvent. In this conjugate acid-base pair, HS, the solvent, is the conjugate base, and H2S plus is the conjugate acid. On the other hand, here, S minus is the lyate anion of the solvent. It is the conjugate base of the solvent. It is produced by proton removal from solvent molecules. In this conjugate acid-base pair, S minus is the conjugate base and HS, the solvent, is the conjugate acid. So here we see that the solvent HS has an amphiteric role. In one conjugate acid-base pair, it acts as a conjugate base, while in another conjugate acid-base pair, it acts as the conjugate acid. For a protophilic solvent, all acids stronger than the conjugate acid of the solvent are leveled with the conjugate acid of the solvent. We can represent this graphically as follows. Assume that the acidity here increases from bottom to top, and the acidity of the conjugate acid or the ionium cation of the solvent is located here. Acid is stronger than the conjugate acid of the solvent, like HA, like HB, are level with the conjugate acid of the solvent. On the other hand, this is not the case with acids weaker than the conjugate acid of the solvent, like HC and HD. Here, the solvent HS is a leveling solvent for acids like HB and HA, which are stronger than the conjugate acid of the solvent, which have higher Brensted acidities than that of the conjugate acid of the solvent. Solutions of these acids at the same concentrations have the same acidities. This solvent HS make these acids appear equally acidic in their solutions. On the other hand, solvent HS is a differentiating solvent for these acids, which are weaker than the conjugate acid of the solvent. The solvent HS can differentiate between acidities of these acids. Solutions of these acids at the same concentrations have different acidities. For example, we expect that solution of HC in the solvent HS to have stronger acidity than that of the HD at the same concentration. Acids like HA and HB, stronger than the conjugate acid of the solvent, are considered as strong acids in the solvent HS. While, on the other hand, acids weaker than the conjugate acid of the solvent, like HC and HD, are considered as weak acids in the solvent HS. For strong acids, acid dissociation reaction is complete. All of acid is dissociated. In other words, equilibrium constant or acidity constant of these acids is so great that almost none of initial acid remains, and all of it is converted to the conjugate base and the ionium cation of the solvent. On the other hand, for the weak acids, the acid dissociation reaction is not complete. All of acid is not dissociated. Their equilibrium constants or acidity constants are small, and not all of acid is dissociated. A significant fraction of initial acid remains in the form of the conjugate acid at equilibrium point. For strong acids, since acid dissociation reaction is complete and none of acid remains, we can assume that reactions which produce the acid are meaningless. Reactions like the base dissociation reaction of their conjugate bases. In other words, equilibrium constants of such reactions which produce the acid, strong acids, are so small that we neglect them. Therefore, we don't consider basic properties or proton accepting capabilities for conjugate bases of strong acids in the solution. We treat them as they are neutral, as they are without proton accepting capability. On the other hand, this is not the case with weak acids. In the case of weak acids, we consider both acid dissociation reaction for conjugate acids and base dissociation reaction for conjugate bases. Based on discussions like these, we can see that in the solvent HS, we can't have any acid stronger than the conjugate acid of the solvent. All acids stronger than the conjugate acid of the solvent are leveled with each other and with the conjugate acid of the solvent. Therefore, the strongest acid that we can have in the solvent HS is the conjugate acid of the solvent, is the ionium cation of the solvent. For example, in water, H2O, the strongest acid that we can have is hydronium cation, H3O+. In ammonia, NH3 as the solvent, the strongest acid that we can have is the ammonium cation, NH4+. In sulfuric acid as the solvent, the strongest acid that we can have is the conjugate acid of the H2SO4. It is H3SO4+, and so on. All acids stronger than the conjugate acid of the solvent are leveled with the conjugate acid of the solvent. We can also consider a similar discussion for bases. In a protogenic solvent, all bases stronger than the conjugate base of the solvent are leveled with each other and with the conjugate base of the solvent. We may represent this graphically as follows. Consider that in this graph, basicity increases from bottom to top. And the basicity of the conjugate base of the solvent is located here. We can have bases stronger than the conjugate base of the solvent, like E-, G-. Also, we can have bases weaker than the conjugate base of the solvent, like D-, C-. The solvent HS is a leveling solvent for bases stronger than the conjugate base of the solvent, for bases which have higher Bronsted basicities than that of the conjugate base of the solvent. The solvent HS can't differentiate between basicities of these bases. Solutions of these bases at the same concentrations in the solvent HS will have the same basicities. The solvent HS will make these bases appear equally basic, appear to have equal basicities. On the other hand, the solvent HS will be a differentiating solvent for bases like C- and D-, which are weaker than the conjugate base of the solvent, which has lower Bronsted basicities than that of the lyeate anion of the solvent. The solvent HS can differentiate between basicities of these bases. Solutions of these bases at the same concentrations will have different basicities. The solvent HS will not make the basicities appear the same. Here, in the solvent HS, bases like G-, E-, stronger than the conjugate base of the solvent, are considered as strong bases. On the other hand, bases like C-, D-, weaker than the conjugate base of the solvent, are considered as weak bases in the solvent HS. For strong bases, we assume that base dissociation reaction is complete. All of base is dissociated and almost none of it remains at equilibrium point. In other words, associated equilibrium constants or basicity constants are so great that almost all of the reactant, the initial base, is consumed. On the other hand, for weak bases, the base dissociation reaction is not complete. Not all of the initial base is dissociated. In other words, associated equilibrium constants or basicity constants are small, and a significant fraction of initial reactants, the initial base remains. For strong bases, since all of the base is dissociated and none of it remains, we can assume that reactions which produce the base are meaningless. Reactions like acid dissociation reactions of the conjugate acids. In other words, the equilibrium constants of reactions that produce strong bases in the solvent are so small that we can neglect them. Therefore, we don't consider acidic properties, proton donating abilities for the conjugate acids of strong bases. We assume that the base dissociation reaction is complete. On the other hand, we treat the conjugate acids as they are neutral, as they are without any proton donating capability, of course, in the solvent HS. On the other hand, for weak bases, we consider both base dissociation reaction for the conjugate base and acid dissociation reaction for the conjugate acid. Based on discussions like these, we can say that in the solvent HS, we can't have any base stronger than the conjugate base of the solvent, stronger than the lyeate anion of the solvent. All bases stronger than the conjugate base of the solvent are level with the conjugate base of the solvent. Therefore, the conjugate base of the solvent, the lyeate anion, is the strongest base that we can have in the solvent HS. For example, in water, in aqueous solutions, the strongest base that we can have is hydroxide anion, OH-. In ammonia NH3 as the solvent, the strongest base that we can have is the amide anion, NH2-. In sulfuric acid H2SO4 as the solvent, the strongest base that we can have is the hydrogen sulfate HSO4 minus. All bases stronger than these light anions in these solvents will be leveled with the light anion of the solvent. We can consider this discussion for a protophilic solvent. We can consider this discussion for a protogenic solvent. And for an amphiprotic solvent, we can combine these graphs to obtain graphs like this. Assume that here acidity increases from bottom to top, or on the other hand, basicity decreases from bottom to top. For the amphiprotic solvent HS, we can consider two conjugate acid-base pairs. Let's assume that the Brensted acidity of H2S plus, the conjugate acid of the solvent, is located here. And the Brensted acidity of the solvent itself is located here. Let's consider this increasing acidity of the conjugate acid. So in fact, here we are dealing with the conjugate acid-base pair, Lionium cation solvent, and we are dealing with the conjugate acid-base pair, solvent liate anion. Different conjugate acid-base pairs can have different positions in comparison to positions of these two related to the solvent. We can have acids, we can have conjugate acid-base pairs like HAA- and HBB-, whose conjugate acid has higher Brensted acidity than that of the Lionium cation of the solvent, or whose conjugate base has lower basicity than the solvent itself. We can also consider conjugate acid-base pairs like HCC-, HDD-, whose conjugate acid has acidity between those of Lionium cation and solvent itself, or whose base conjugates have basicities between those of HS and S-. We can also consider conjugate acid-base pairs like HE- and HG-. Whose conjugate acid, He and Hg, has lower acidities than that of the HS, or whose conjugate bases, E-, G-, have higher basicities than that of the liate anion of the solvent. Based on our previous discussions, we can discuss that these are strong acids. Here, conjugate acids are strong acids. Their acid dissociation reactions are complete. For example, HA yields H plus and A minus completely. In fact, these reactions are equilibrium reactions, but their associated equilibrium constants are so great that we assume they are complete. On the other hand, we treat their conjugate bases as they are neutral. In the solvent HS, and we don't consider base dissociation reactions like this for them. In this case, for conjugate acid-base pairs whose conjugate acid is weaker than the solvent as an acid, we consider that the conjugate bases are strong bases. And we assume that the base dissociation reaction is complete. For example, we assume that this reaction for the base E minus is complete. On the other hand, we treat their conjugate acid as they are neutral. And we don't consider acid dissociation reactions for them. In the case of these conjugate acid-base pairs, whose conjugate acid has acidity between those of the HS and H2S plus, we consider conjugate acid as weak acid, and we consider equilibrium reactions for their acid dissociation reactions. On the other hand, for them, we consider conjugate bases as weak bases, and consider base dissociation reaction for them in the form of equilibrium reactions. So we see how we may treat different conjugate acid-base pairs with different acidities and basicities in the solvent HS. Here we have a very important discussion. Here we can see that if the acidity of the solvent HS increases, the solvent can be a leveling solvent for more bases. It can be a leveling solvent for weaker bases. On the other hand, if the basicity of the solvent increases, this space above this increases, so the solvent can be a leveling of solvent for more acids, for weaker acids. In other words, solvents with higher acidities are leveling solvents for more acids, for weaker acids. And solvents with higher basicities are leveling solvents for more acids, for weaker acids. We can also say that to have a differentiating solvent for strong bases, we should consider solvents with lower acidity. On the other hand, to have a differentiating solvent for strong acids, we should have a solvent with lower basicity. In other words, solvents with higher acidities enhance the basic properties of chemical species, enhance the proton accepting capability of chemical species, while solvents with higher basicities enhance acidic properties of chemical species, enhance the proton donating capability of solutes. For example, when acidity of the solvent increases, the basic properties of chemical species increases. For example, a non-electrolyte may become a weak base. A weak base may become strong base. On the other hand, when the basicity of the solvent increases, it enhances the acidic properties of chemical species, of solutes. A non-electrolyte may become a weak acid may become a strong acid, and so on. Let's consider examples for this. Consider ammonia NH3 as the solvent. It is an amphiprotic solvent. Its autoprotolysis is as follows. Its conjugate acid is the ammonium cation. Its conjugate base is amide anion. Ammonium cation is the strongest acid that we can have in ammonia. All acid is stronger than ammonium cation will be level with the ammonium cation. Amide anion is the strongest base that we can have in ammonia. All bases stronger than the amide anion will be level with amide anion. For example, perchloric acid is an acid stronger than the ammonium cation, the conjugate base of the solvent. So in ammonia, perchloric acid has complete acid dissociation reaction and it is level with ammonium cation. On the other hand, H-, the hydride anion, is a base stronger than the amide anion, the conjugate base of the solvent. So in ammonia, the hydride anion is leveled with the amide anion. This base dissociation reaction in ammonia is complete. All of the hydride anion is converted to the amide anion. In comparison to water, ammonia as the solvent is more basic. Brensted basicity of ammonia is higher than that of the water. So, ammonia enhances the acidic properties or proton donating ability of solutes. For example, acetic acid is a weak acid in aqueous solutions, but it is a strong acid in ammonia. And this reaction for acetic acid, this dissociation reaction for it in ammonia is complete. As another example, urea in water is almost non-electrolyte without acid or basic properties. But in ammonia, its acidic properties is enhanced, and urea in ammonia is a weak acid. And we can consider acid dissociation reaction for it like this. As another example, let's consider sulfuric acid as the solvent. Sulfuric acid is an amphiprotic solvent. It has autoprotolysis as follows. The Lionium cation of the sulfuric acid is H3SO4+, and its liate anion is HSO4-. All acid stronger than the Lionium cation will be level with the Lionium cation, and all bases stronger than the liate anion will be level with the liate anion. In comparison to water, sulfuric acid is much more acidic. The Brensted acidity of sulfuric acid is much greater than that of the water. In fact, it is hard to find acids stronger than the conjugate acid of the sulfuric acid. On the other hand, there are many bases stronger than the conjugate base of the sulfuric acid. So many chemical species behave as strong bases in the sulfuric acid as the solvent. Sulfuric acid enhances the basic properties or proton accepting abilities of many solutes, and many solutes act as strong bases in sulfuric acid. Weak and strong bases in water, aqueous solutions, become strong bases in sulfuric acid. Non-electrolytes or even acids in aqueous solutions may become strong bases in sulfuric acid. For example, urea is a non-electrolyte in water, but it is a strong base in sulfuric acid as the solvent, and its base dissociation reaction here is complete. Acetic acid is a weak acid in water, in aqueous solutions, but it becomes a strong base in sulfuric acid. Its base dissociation reaction, this reaction in sulfuric acid, is complete. Nitric acid is a strong acid in aqueous solutions, but it becomes a proton acceptor in sulfuric acid. We have this reaction for it in sulfuric acid. Here it is good to compare acid-base behavior of the same species at different solvents. For example, consider acetic acid. Acetic acid as our solute in the water in aqueous solution is a weak acid. In the solvent ammonia, a more basic solvent than water, acetic acid is a strong acid. Its acidic behavior is enhanced. On the other hand, in the solvent sulfuric acid, which is much more acidic than water, acetic acid is a strong base. Its basic properties are enhanced. As another example, consider urea. Urea in water in aqueous solution is almost non-electrolyte. It neither accepts proton nor donates it. But in ammonia, a basic solvent, its acidic properties are enhanced and it becomes a weak acid. On the other hand, in sulfuric acid as the solvent, urea becomes a strong base. Its basic properties are enhanced. So here we see how discussion and rules for different amphiprotic solvents are similar, and also we see how acid-base behavior of the same species might change when the amphiprotic solvent changes. Or we see that how acid-base behavior of species depend on the acid-base behavior of amphiprotic solvents. Finally, here it is good to mention that in some of these discussions, in addition to the acidity or basicity, we should consider the effect of concentration. We discussed that strong acids are acids whose acid dissociation reaction is complete. We usually assume that acids stronger than the conjugate acid of the solvent are strong acids in that solvent. However, if we want to be exact, we should also pay attention to concentration. Consider the following relationships. Consider the acid HA in the amphiprotic solvent HS. Its acid dissociation reaction will be as follows. Its acidity constant in terms of equilibrium concentration will be as follows. Let's assume the initial concentration of HA to be C, and let's assume that its degree of reaction, its degree of dissociation, the fraction of acid which is dissociated at equilibrium point is alpha. Therefore, at equilibrium, the equilibrium concentrations will be as follows. If we substitute these equilibrium concentrations in this relationship, we will have if we omit C from top and bottom, we will have, or we will have therefore Ka is the acidity constant of the acid, C is its initial concentration, and alpha is the fraction of the acid which is dissociated. Let's assume that alpha greater than 0.99 means almost all of acid is dissociated. So acid is a strong acid. Alpha over 0.99 means that 99% of acid is dissociated and only less than 1% of it remains in its undissociated form. So it seems reasonable to assume that for alpha greater than 0.99, almost all of acid is dissociated and acid is a strong acid. If we substitute this here, we will have so if the ratio of acidity constant to the initial concentration of acid is greater than 98, about 100, the degree of dissociation, the fraction of acid which is dissociated, will be greater than 0.99, and we can assume that acid is almost completely dissociated and acid is a strong acid. To have this inequality true, for Ka equal to 1, we should have initial concentration of acid smaller than 0.01. For Ka equal to 100, we should have the initial concentration of acid is smaller than 1.02. For Ka equal to 1000, we see that we should have the initial concentration of the acid is smaller than 10.2. We know that acids stronger than the conjugate acid of the solvent has acidity constants greater than 1. Based on these examples, we see that for acids which are much stronger than the conjugate acid of the solvent, for example, the acidity constants is greater than 1000, even at high concentrations, this inequality holds true, and we can assume that acid is a strong acid. But for acids which are a little stronger than the conjugate acid of the solvent, their acidity constant is close to 1. We see that only at low concentrations this inequality holds true, and acid has complete acid dissociation. Therefore, we see that for acids like hydroiodic acid, whose acidity constant is much greater than 1, which is much stronger than hydronium cation in aqueous solutions. At any concentration, we can assume that its acid dissociation reaction is complete. On the other hand, in aqueous solutions, for acids like nitric acid, whose pKa is about minus 1.7, its Ka is not much bigger than 1. We see that only at low concentrations, the acid behaves as strong acids. Anyway, since many acids stronger than the conjugate acid of the solvent usually have acidity constants much greater than 1, it is common to say that acids stronger than the conjugate acid of the solvent are strong acids. And it is common to assume that the acid dissociation reactions are complete. However, if we want to be exact, we should consider that for acids which are a little stronger than the conjugate acid of the solvent, only at low concentrations acid behaves as a strong acid. Acid dissociation reaction is complete. And at higher concentrations, it will behave as a weak acid. This inequality has other side. We know that for acids weaker than the conjugate acid of the solvent, Ka is smaller than 1. But here, initial concentration of the acid can be too small, so small, that this inequality, despite the small value of Ka, holds true. Therefore, we see that acids weaker than the conjugate acid of the solvent may act as strong acids, may have complete acid dissociation reactions at very low concentrations. So we see that in general, if we want to be exact, concentration is also important. But usually, we can approximately say that acids stronger than the conjugate acid of the solvent are strong acids, and acids weaker than the conjugate acid of the solvent are weak acids. Where for strong acids, acid dissociation reaction is complete, while it is not so for weak acids. We can also consider a similar discussion for bases. This is the end of this online tutorial. I hope you find it useful.